All right, welcome back to linear algebra. Let's jump into Anki before I recall what we did yesterday. Okay. What is a trace of a square matrix and how is it denoted? Trace is not the transpose. The trace is the sum of the entries in the main diagonal of a square matrix. How's it denoted? It's denoted the power. No, it's actually denoted like a function almost, like TR, and then within the parentheses you have the matrix. What is a linear combination of matrices? A linear combination of matrices. This is like a large sum of matrices, right? Large sum of matrices. An expression in the form of C1A1 plus C2A2 plus CRAR, where C1, CR scalars and A1, AR matrices the same size. Okay, we're gonna say no. What are the commutative law? What are the commutative law of addition, the associative law of addition, and the associative law of multiplication, and left and right distributed laws for matrices? Commutative law of addition, A plus B equals B plus A. You can move them around. Associative law of addition, A plus B, the sum of A plus B plus C equals A plus the sum of B plus C. The associative law of multiplication, the product of A times B times C is equal to A times the product of B times C. And the left and right distributive laws for matrices, if you got the matrix on the left side and it says A times the sum of B plus C, then it's going to be AB plus AC. If A is on the right side, it's going to be BA plus CA. It is proved in the text that the inverse of an invertible matrix is also invertible. How is A related to the inverse of A? It's A. If R is the reduced row echelon form of a square matrix, and if R has no zero rows, if R is a reduced row echelon form of a square matrix, and R has no non-zero rows, then what must be true if the matrix R is equal to I? If A is an invertible matrix and N is a positive integer, what does the symbol A to the power of negative N denote? Denotes the inverse of A times the inverse of A times the inverse of A N times. Right. A linear combination of matrices is a sum of matrices in the structure of C1 A1 plus, it's an expression in the structure of C1 A1 plus C2 A2 plus ... plus Cn AN, in which C1 through Cn are scalars and A1 through AN are matrices of the same size. Okay. All right. What did we learn about yesterday? Okay, we learned about diagonal matrices, triangular matrices. We did not start symmetric matrices yet. So diagonal matrix, this is a matrix in which all of the entries that are off of the main diagonal of a square matrix are equal to 0. That's a diagonal matrix. So a zero matrix is a diagonal matrix. A diagonal matrix is invertible only if each of the entries in the main diagonal are non-zero. the product, the power of a diagonal matrix. So a to the k, each of the entries is simply raised to that power k. Really in the main diagonal only because all the other zeros will still be 0. Multiplying by a diagonal on the left. If the diagonal matrix is on the left, then basically you're just going to take the top entry in the main diagonal and multiply by each of the top row of the second matrix, and you're going to go row by row. If it's on the right, I think you're going to go column by column. Triangular matrix. A triangular matrix is a square matrix again. That's either an upper triangular matrix or a lower triangular matrix. A lower triangular matrix is a matrix in which all the entries above the main diagonal are 0. An upper triangular matrix is a matrix in which all the entries below the main diagonal are 0. Now we had some properties of these triangular matrices. I believe I think it's again, it's only invertible if the main diagonal is all non-zero. The inverse of an invertible lower triangular matrix is a lower triangular matrix, and the inverse of an invertible upper triangular matrix is an upper triangular matrix. Two lower triangular matrices multiplied together is a lower triangular matrix. Two upper triangular matrices multiplied together is an upper triangular matrix, I believe. Talking about inverses, if invertible, multiplication. What was the other? I think I forgot this one the last time too. What could it be about? Summing, no. Subtracting, no. Inverting, we already talked about inverting a little bit. It could be another thing about inverse. Power? No, I don't think so. We'll find out. Product of two. Transpose. Transpose of an upper triangular matrix is a lower triangular matrix. The transpose of a lower triangular matrix is an upper triangular matrix. Okay. Diagonal matrices, invertible, okay, power, if positive, true, but it also, I think it works if it's negative, but you take the inverse first. Multiplying by diagonal, okay, left equals row, right equals column, great. Triangular matrix, good, and then, yeah, the transpose, so everything else is good. I'm going to jump back in to continue reading now, and then I'll be back to recall what I learned in a little bit. All right, we just finished 1.7. What was even 1.7? Oh, I didn't even write down what it was about. It was about triangular, symmetric, and diagonal matrices. Okay, so we just read a lot about symmetric matrices. What is a symmetric matrices? Or a matrix? Symmetric matrix is a matrix in which the transpose of itself equals itself. To spot a symmetric matrix using just identification, just looking at it, first it needs to be a square matrix. So I don't know if I said that. A symmetric matrix is a square matrix in which transpose equals itself. Okay, so you look at it, is it a square matrix, yes or no? Yes. Then you look at the entries that are mirrored across or over the main diagonal. If those are equal, then you got a symmetric matrix that doesn't matter what is in the main diagonal because it's going to be the main diagonal either way when you flip the rows and columns or vice versa. All right. We got some properties of these things. What are they? What are some of these properties of symmetric matrices? If you got a symmetric matrix, then then the transpose is also symmetric. Also, K being a scalar times the matrix is symmetric. If A is a symmetric matrix and B is a symmetric matrix, then A plus B, that's a symmetric matrix. B plus A, that's a symmetric matrix. A times B or B times A, not necessarily symmetric, but if it is if and only if A and B commute. All right. Okay. I'm forgetting some stuff. However, we also there was a section in there about basically when you take a matrix times its transpose of itself, it always produces a square matrix, and it's always symmetric, which is it's interesting. They mentioned there's gonna be a lot of applications for that, or there are. So, oh, they're also. Oh wait, no, I said invertible. I meant to say symmetric, square and symmetric. Okay. Oh wait, yeah, symmetric matrices are not always invertible, but if they are, what do we know? There's something we know. If a symmetric matrix is invertible, then its inverse is also symmetric. And if A is invertible, then itself times its transpose, or its transpose times itself, is also invertible. Okay. If A is symmetric, so is transpose. Yep. Okay. If A and B are symmetric, good. All right. That's it. That's the chapter. What's it about? It's about diagonal, triangular, and symmetric matrices, what they are, and some properties. Okay, that's it. Yeah, that's gonna wrap it up for today. Tomorrow we'll actually get into the problem set. It's a big problem set, but really cool. And now we are through another section and into the problem set. We are, let's say maybe just about just a little under 15% of the way through the textbook, but we're moving faster now. That's it for today. Talk to you tomorrow. See you.